אם אני נתקעים, אני אתן גם זה. יש מקומות יותר גרועים את הקרמה. מקומות יותר גרועים.
מה הצלחנו להוסיף? הצלחנו 5 סוף אחרון.
מה זה? הצלחנו לא לשאול. לא חשבנו.
מה קורה?
גיא, שאלה. הסתכלתי כזה על... כן, נכון, חיפשתי ביום ראשון, ואז לא ראיתי אותך, אז כבר שמעתי מיערי. אז קיבלתי את התשובה. רציתי לשאול, אז יש כזה את ההוכחה של שורס למה, נכון? ויש שם את לייצר את הפרוג'קשן הזה. אז זה כאילו, זה טכניקה שמשתמשים בה באופן כללי, שאם אתה רוצה לייצר פונקציה שהיא בעצם לא רציפה, אז עוברים לדבר הזה של לעשות, ומחפשים משהו.
כן, בגדול, אוקיי, לא דיברנו על אלגברות פונומן, אלגברות פונומן לא קומוטטיביות, הן בדיוק, אלגברות פונומן קומוטטיביות הן בדיוק כאלה אינפיניטי של מרחב מידע. וגם התכונה הזאת של, נכון שבמרחב רציף אין לך מספיק פרויקט, במרחב טופולוגי, פונקציות רציפות על מרחב טופולוגי לא מייצרות לך לרוב פרוג'קשנים, כי לרוב אין לך קלופנסס, פאצורבר. אז צריך לעבור לאיזשהו בורל, סמכי אינפיניטי כזה.
תודה.
טוב, אז בפעם שעברה, היי יונתן, בפעם שעברה דיברנו על GNS, נכון? ראינו שכל בהינתן state, phi, אנחנו יכולים להרכיב ממנו הצגה, phi phi, h phi, in vector ציקלי, כך שבעצם אפשר לומר שהפי הזה הוא מתנפח להצגה הזאת, כלומר, I need to depress to English because there are some indistinct duels, so this phi dilates to this prism, or if you want, it's a compression of this down movement. And okay. And so this is GNS, and this was the last. And we also obtained from the GNS this universal representation of any sister algebra, right? We can always take the direct sum over all the states. This will be faced. Now, somehow there are too many representations here, and maybe we can do something better. So this is one thing. Another thing, I mean, in general, this set has an extra structure that we may want to consider. So the set is not only a compact set, it is clear that it is compact with respect to the Weizmann topology because of the Banach-Alaoglu theorem, which tells us that the unit ball of the continuous functionals of array with respect to the Weizmann topology is compact, so this is a closed subset of it. But it is also convex. So this is something you show in your homework. Therefore, by the Weizmann theorem, any compact convex set is the convex hull of the extreme point of this set. So we call the extreme point of this set of the state space of A pure states. So definition, this is also a part of the homework, but okay, maybe let me just write it like this. In the homework, you show, or we show that SA is a convex compact set. We call its extreme point. Hence, it has extreme point, and we call its extreme points pure states. By Weizmann, the state space of A is the convex hull, the closed convex hull of the pure states. Okay. And so let's do some examples, perhaps. So examples. So I remind that the state space of continuous functions over a compact Hausdorff space is nothing but the probability
measure.
No, you're jumping
the pure
to the pure states. Did I ask you to prove what are the pure states of the? No, I didn't, right? I did. Okay. So this is well, phi from here is nothing but is just phi of f f mu, right? For mu probability. So we can in fact identify state space of C of x and probability measures over x phi pure. If and only if, as you said, mu is just the Dirac function. So it makes sense, I think. But if you don't see it, there is something to prove, right? Because the fact that you are infinite convex combination of points does not mean that you are like, well, a priori. You should think why it means you are finite convex. Okay, but this will improve. So exercise. So you don't see it. I mean there is something to show even if you see it. And another example. So the other example for states what I mentioned was phi state space on Mn, right? And I remind you that these are exactly functions of the form phi a, where A is an n by n matrix, and phi a of t is the trace, the usual trace of AT. And A is positive, definite, and its trace has to be 1, so it could be a state. So these are just states, and they are true if what? So obviously, if I can write a matrix here as a convex combinations of two other positive matrices, then, well, with phrase 1, then this phi would be a combination of 2 other states of this form. So I need somehow to remove this option. So think about it. So phi is pure if and only if A has rank 1. And then it has to be a projection. So maybe let me write it like this. A is a rank 1 projection. A rank 1 projection. Projection. Okay. So this is also.
So pure state can be thought of as just a vector.
Yes. Okay. So theorem. Phi is pure state. Maybe let phi be. Let it be sister algebra. Phi state. Then phi is pure if and only if phi is irreducible. So I remind you that irreducible star representations are those representations that doesn't have a proper non-trivial closed invariant subspace. And we showed that this is equivalent to have a non-trivial commutant, to have somebody in your commutant, somebody that commutes with any pi phi of A. Okay, and this is one thing. The other thing is that, okay, something we didn't prove, but maybe it's good at least to let you know. We will not do it, but I just want to tell you about it. So, of course, we can define irreducibility in an algebraic way, to say that there is not even invariant subspace, proper invariant subspace that is not trivial, not necessarily closed. Surprisingly, these two notions of algebraically irreducibility and irreducibility are the same. We coincide, but it's hard to prove. It's not really difficult. I mean, I need 45 minutes also to do it, but I won't. But just for you to know. So this tells us, this explains why last time I told you that in the GNS construction, you don't have to complete A mod n in case phi is pure. I just mentioned it in somebody asked, and the reason is, of course, because this is reducible, but it is also algebraically reducible.
So it's already complete?
Yes. But in general, no, but for pure states, yes. Okay, so let's do it. So proof. Assume first that pi phi is not reducible. Then there exists a projection in pi phi A prime, such that pi is not P is not 0 or 1, right? Let. So this is by what we showed, I think, for two times. 2 classes ago. Let Yes. So I'm going to jump to the end for a second, and then I'll go back and tell you what I'm going to define. So then there will be then somewhere here. And what we in A, phi of A, which is psi phi pi A psi phi is where I just want to add here P plus I minus P, identity minus P, P plus identity minus P, pi phi with psi phi. I'm going to get the convex combination and then I'll define everything. So I'll go back. Okay. So this P is going to give me a convex combination here. Okay. That will be non-trivial. So this is right. Whenever I have, so I'm going to write. I'm going to break it into 4 sums. But 2 of these sums are going to vanish, right? Because whenever I multiply P with I minus P, then these are orthogonal, because these are orthogonal projections. So we will remain with P psi phi, P pi phi psi phi, pi phi psi phi, plus I minus P psi phi, I minus P pi x psi phi. Right? Does this look like a convex combination to you? Well, so first let me write pi is in the commutant, P is in the commutant. So I can flip these 2 guys and also these guys. So this is just pi pixie phi P pixie phi pi phi A pixie phi. Good, this is what I wanted. Plus I minus P C phi pi phi A I minus P C phi, and let's make this like a unit. Let's make it a unit vector, so that this will be a state. So it means that in psi I need to divide by pi psi phi square. So I need also to fix it outside. So now this is a state. This is a vector state. And I'm going to do the same thing here. But if this is a convex combination, so I need this guy plus this guy to be 1. This is Pythagoras, right? Good. So okay. So now we need to go back to fill a few details and to explain why these guys are not trivial convex combinations, and then we finish one direction of the proof, right? Do you have any questions? Is anything not clear? I assume that the pi phi is not irreducible. I took a P in the commutant. This is equivalent to being irreducible. This is something we proved. And then from it, somehow we managed to decompose phi into two states. Why is this a state? Is it clear?
No.
No, because whenever you take a unit vector, so for any unit vector eta, and for any representation A, this is a state. So, and this was not a unit vector, but after I divide it by the norm in each place, then it is. Where's the question? Okay, sorry. Okay, so this was our very third example of a state. Okay, so let me just fill it. Let alpha be pi psi phi square. I want first to show that alpha is non-zero and not one. Clearly, alpha is between 0 and 1. If alpha were 1, then it means that P xi phi is xi phi without the norm. Why? Because then pi psi phi is psi phi. Why?
Triangle inequality.
Something like this, yes, right? Because psi phi square by Pythagoras is pi psi phi square plus I minus p psi phi square, right? But if these are equal, then this is 0. So this thing inside is 0. So we have this. Okay. So, and then what's the problem? Psi phi is cyclic, and P commutes with pi phi of A. So this will tell us that pi is the identity, that P is the identity. So, but then, write P of pi A psi phi, which is equal to pi phi A of psi phi, sorry, of P of psi phi is equal to pi phi A of psi phi, because these are equal. But this is dense in H. So the image of P is dense in H. So P has to be the identity. So P is 1. Is pi phi A, psi phi is everything. Good. And if alpha is 0, then the same argument will show that P is 0. Right, but it is not. If alpha is 0, similar argument shows P is 0. So now we know that alpha is strictly between 0 and 1. So this is a proper convex combination, right? This guy is alpha. This guy is 1 minus alpha by the Pythagoras, by this. This is a proper convex combination of states, since alpha is between 0 and 1. Now, the last thing that we have to verify is that these two guys are not the same. Like maybe this is equal to this, which is equal to, right? And then, okay. So let me call this psi 1 of A, and this is psi 2 of A. It remains to show psi 1 is not equal to psi 2. So what is psi 1 of A minus psi 2 of A? Psi 1 of A minus psi 2 of A for every A in A. Let's write it. This is so we're going to write it. Check. So yes, so right, so this is let me call this alpha, okay, this denominator. So I have here nothing but 1 over alpha pi psi phi minus 1 over 1 minus alpha 1 minus phi psi phi, comma pi a pi phi x psi phi. So okay, so here in fact I should have written something like pi phi plus 1 p right here. Here there is a secret p plus 1 minus p. And if you open it, then you'll get this thing. Because all the guys that are p times 1 minus p and this will vanish. Now forget about the red guy. Call this guy eta. Call this vector eta. Then eta is, so if these guys are the same, then eta is orthogonal to everything because it is orthogonal to the n subset. So if psi 1 is equal to psi 2, then eta, which is 1 over alpha pi p psi phi, I don't know why I call today to p pi, right? Is orthogonal to pi phi a psi phi. And if you're orthogonal to something, then you are orthogonal to its closure, and then you're orthogonal to all of H. So therefore this is the 0 vector. So eta is 0, and since I take eta is 0, then this means that what? Well, this can't be the case, right? Because these are orthogonal vectors. So orthogonal vectors are linearly independent. They can't be, but p psi phi and 1 minus p psi phi are orthogonal, and in particular, and therefore linearly independent. Because some noise from here. Wait a second. Hi, Tamar. And therefore, eta is and therefore linearly independent. Linearly independent, and therefore so contradiction. Okay, so we are done with one direction. Okay. Questions about this direction? Please feel free to stop me, to ask questions.
You would explain why this show is not pure?
Yes,
maybe
because it's not. So being pure means that you are not, that your extreme point Being extreme point means that I can't write you as a convex combination of two other guys. So I showed.
Does it need to be for every A?
Yes. So by writing phi is equal to T, I don't know, alpha psi 1 plus 1 minus alpha psi 2, I mean that for every A, phi of A is equal to alpha psi 1 of A plus 1 minus alpha psi 2 of A. Being an extreme point means, by definition, that you're not of this form. That I can't find psi 1 and psi 2 in alpha that is strictly between 0 and 1, such that I'll be able to write phi like this. So I show that if P is irreducible, if phi is irreducible, if phi is irreducible, then I can write. I am able to write phi as a proper convex combination. So phi is not Q. So we showed here that phi is not Q. Okay.
I'm confused about the for every A. So if you want to contradict, if you need it for some A, just show.
No, I didn't show anything here. I just said for every A we have this.
Yeah.
So if psi 1 were equal to psi 2, then this means that this vector is independent of A, right?
Mm-hmm.
There is no A inside. So this vector eta is orthogonal to each guy of this form. So it is orthogonal to all of the space because the closure of this is H. So now we need to prove the other direction, right? Okay. Conversely, assume that phi is not pure. I will show that phi is not reducible. Okay. Assume that phi pure is not pure. Let's write it as let's decompose it. That's alpha be between 0 and 1, and psi 1, psi 2 between states, and not equal states, right? Such that phi of A, such that phi is alpha psi 1 plus 1 minus alpha psi 2. Define, so I'm going to use a trick that is similar to things that we did before. Define a sesquilinear form using psi. So it's going to be something like this. Okay, so I'm going to define it on a dense set. Okay, so I'm going to tell you what it does to pi a of psi phi times pi b psi phi. It's going to be alpha psi 1 of A star. So we need to show this is well defined first, right? Because maybe it's not well defined, but know that pi phi A, well, if I take B to be A, then I get alpha of psi 1 of A star A. These are states. So in particular, they are positive. And phi minus alpha psi 1 is also positive. and A star A is positive. So therefore, this guy has to be less than or equal to than phi of A star. But this is, right, this is just psi phi, pi phi of A star. Psi phi, which is equal to pi phi of A psi phi norm square. So what? So if I take somebody here that is 0, then this guy will be 0. Right? Because this is equal to this, then this is also positive. It's great. So if a vector has a 0 representation somehow, then this Esquilino form would think about it as a 0. Right? We're using sort of a Schwartz that we have for Esquilino forms. So in particular, if pi xc is 0, then pi phi of A psi phi, pi phi of A psi phi is 0. So for every b in A, in this case, pi phi of A psi phi, pi phi of B psi phi would be 0 by the Cauchy-Schwarz. So this tells us that this is well defined. Maybe let me write it like this. It's a well defined, bounded, Esquilino form in our positive form. And therefore it extends to such on H, which is the closure of this. So H is pi phi of A psi phi closure, so it extends to such. So I can find a positive operator. So there exists a positive operator in B of H such that for every U and V, maybe for every sin eta psi eta is equal to psi t eta in a product. Right? So now I'm claiming that I'm done. This T sits in fact in the commutant of A, of pi phi of A, therefore pi phi is not irreducible. So all the questions up until here because I'm going to erase this part. So again, what I'm going to show now is that T commutes with pi phi of A. This is just an easy exercise, and we'll do it. So I can erase this part. And we get to claim inside the proof, T is in pi phi of A prime. Proof of claim. So I can show it on a dense. Okay, so we need to show that let's say that for every in A, psi t minus pi a of eta sorry, something like this. T pi a minus pi a t of eta is 0 for every sine eta, right? But it's enough to show this on a dense subset. So, but enough to show for every b and c in A that pi of b psi phi t pi a minus pi a t pi c of psi phi is 0. Now we just need to open everything. But so let me write it over here. But this guy, let me call it psi, okay? That phi. Okay, I open this and remove this pi a here in the second summand, and now these will be linear form. So this is pi b sine pi a c sine minus this is linear form pi a star b sine pi c sine. So this is just psi alpha. Alpha of psi 1 of b star of do we take the star of the first or second I forgot? How did I write this? Yes, like this, right? Okay, so b star ac minus alpha psi 1 of the star of this. Okay, so let's just check that t is not a scalar. So I'm done with the proof of the claim. And back to the proof of the theorem. Back to the proof of the theorem. If t were lambda I, lambda 1, then what? What's the problem? Then what is alpha? Let's say what is alpha 1 times what is alpha psi 1 times a star b or b star a? This is by definition the right the pi b of psi phi times pi a of psi phi, which is the truly inner product of pi b psi t pi a psi, but t is just a lambda now. So t maybe t pi a psi, but t is just a lambda. so this is lambda times psi pi b star a psi. But this is phi. This is lambda phi b star a. So if psi 1 is phi, it means that that also psi 2 will be phi, and the convex combination was trivial. But so C1 and phi are dependent, are linearly dependent. And so are equal, because they are states, and also equal to which is a contradiction, because somewhere I assumed that it is not. Okay. So if we now go back to the so we're done. Do you have questions? Okay. So now, so we showed what? We showed that the GNS representations of pure states are irreducible if and only if the pure, sorry, GNS representations of states are irreducible if and only if the states are pure. So in some sense, you can also think about irreducible representations as sort of extreme representations, maybe, I don't know. Okay, so you also showed in this homework that for every positive element, you can find pure representations that gives you the norm of this guy. So a remark, you also show in the homework that for every unital sister algebra and A positive in A, there is a pure state phi such that phi of A is equal to the norm of A. And this is true also without the unitality assumption. Why? Because if you do it on the unitization and phi was pure on the unitization, then phi has to be pure in A without taking the unitization. Because if phi decomposes as a linear combination in A, of states in A, not a linear, as a convex combination, then you can leave this convex combination to the unitization and to verify that in fact it can be the case if phi was pure in the unitization. Okay, so note that if A is non-unital, and A and phi is a pure state, on A plus, such that phi of A is the norm of A, then phi restricted to A is also pure. Is the exercise. I mean, this is just one line to verify that what I said is true. So we always have this. So as a corollary, every sister algebra. Last time we showed that every sister algebra has a faithful representation on some B of H. Now I claim a bit more than that. I claim that I can require this faithful representation to be direct sum of irreducible ones. Right? Every sister algebra A admits faithful irreducible. No, sorry, not irreducible. Faithful star representation that decomposes into a direct sum. Irreducible. Reducible representations. Proof. And let I be the direct sum over all the pure states. Phi is a pure state. Maybe I just need to explain. I mean that's the end of the proof, but maybe something we did this last time, but maybe let me just clarify and note that for every A, in A, if phi is the pure state, giving A star A its norm, if phi is a pure state such that phi of A star A is the norm of A star A, then phi feed of A star A, then pi phi of A norm square is pi phi of A star A is right side phi well, sorry, I wanted to write something like this. This guy on psi phi, this guy, and square is greater than this guy psi phi square, which is psi phi by phi of A star A, psi phi, which is phi of A star A, which is the norm of A star A, which is the norm of A square. In particular, pi phi over A as the norm of A. So we did this explanation also before for non-pure state. I only wrote this explanation to verify that you see that why is this faithful? Okay. So each summoned here, each element A as somebody here that on which it would be isometric. So the isometric can do that. Okay. So two things that I want to do before the break. One is to think with you about this. So why is this corollary morally better than what we had last time? So last time we said that we have this representation which is direct sum over all states. Why it's better to have only pure states? Of course, this is a smaller direct sum, so it's better in a sense. But not only that, so right, in some sense, in the commutative case, irreducible representations are exactly the points of X, the evaluation, right? So I can think of them as points of X. So in some sense, this theorem tells us that irreducible representations know everything, also in the non-commutative case, about our algebra. Right? I can, if I take the direct sum of all irreducible representations, it's faithful. So it sees all the algebra, like in the commutative case. In the commutative case, it's just to say that the points of X knows who X is, more or less. So
but in the abelian case, we had like 3 images we can also take, and now not, right? It's only faithful, but it is not like there are operators that won't be for any element in the algebra, right?
Again, say again.
The image is not everything. So here.
Well, the image is everything. I mean, what is everything here?
Mm-hmm.
The image of this
Mm-hmm.
is a sister algebra, which is isomorphic to this sister algebra.
Mm-hmm.
I mean, right? It's not so. Each ingredient here has some kind of. Well, I'm not sure I understand that.
In the abelian case, we had like all the continuous functions on our elements, right?
No, it's not the same. No, I'm not claiming this theorem is a kind of a version of the Gelfand transform.
Here it is only an embedding. We don't have a.
Right. It's like right. Yes, I'm not claiming this. I'm just claiming that maybe morally this tells us that like points knows everything about the sets in which they live. Here the points should be irreducible representations, and they know everything about the sister algebra. So it seems that the irreducible representations of A knows everything about A. Does it? I mean, well, the fact that the direct sum of all irreducible representations, I mean, is faithful, does not imply that they know everything about know about A somehow. So let me share with you an open problem, and then we take a break. So an open problem, it's called the Stern-Weierstrass conjecture. This goes to 80 years ago. So maybe 70 years ago. Maybe 80, something like this. 75. So if so exercise, easy exercise, if so before the exercise, let me just say, assume that A is a sister algebra that sits inside B, containing one of B. Sister algebras, okay? If A points, if A separates states of B, meaning that for every phi different than psi states in B, I can find an A in A that will show me this. So if points in A separates SB, then it means that A to be all of B. A has to be all of B. This is an easy exercise. So the conjecture is if A happens to separate only pure states of B, then A is equal to B. So okay, it's a conjecture. Let's verify we understand it in the commutative case. What happens in the commutative case? If B is a commutative, so it is of the form C of X, then pure states of B are exactly delta X's. Then if one is in A, which is in C of X, and A separates and pure states of A, pure states of C of X, it means that then for every X different than Y in X, there exists a function in A, right? A is a subset of functions, such that f of X is not f of Y. These are the assumptions of the conjecture. So can we prove that the conjecture holds in this case? This is the algebras. So the conjecture is true in the quantitative case due to standard. Great. So this conjecture is a reasonable generalization of standard algebras to any Italian, and it is still open. So we can try to prove it. I can tell you about. I mean, like every 10 years, you see an important paper about this conjecture. The first paper was, I think, of Gleam from the 50s. I mean, the very first, in which it showed that if you assume a bit more than pure states, I don't know if it is a bit more, but you take the closure of the pure states in the weak star topology, not the hull, because then you get everything, then it's the exercise. But if you just take the closure, then it is true. Then if A separates the weak star closure of pure state, then so after a few years, there was like in the 70s, more or less, there's a paper of Bunce, really nice one, showing that if A happens to be nuclear, well, we didn't discuss yet about nuclear sister algebras, but then it's also true. But in general, I mean, this is more or less the best thing we don't know enough about it. So you can think about it. And just something I'd like you to also, another way to think about it. So this is equivalent to say that if the irreducible representations of B are separated by points of A. In fact, we can translate all of these discussions from states and pure states to representations and irreducible representations. So remark, and this is also an easy exercise, or not easy, but an exercise. I mean, you can do exercise, you can solve it, comes from the GNS. Remark, the conjecture, the separation assumption in the conjecture is equivalent to separating and irreducible star representations of. So you can think of it like this. So I mean, the reason I explain this is because of this question. Because if if A separates all the representations of B, then A is equal to B. This is easily can be seen. But if A separates only the irreducible representations of B, then it's an operator. Okay, let's take a break. And we are done with sister algebra for now.
רציתי לשאול מה היה בשיעור האחרון באלגברות לי.
בעיקר הצגות של SLM.
הצגות של SLM? SL2 כאילו בטח יצא?
והיה גם אוניברסל אלג'ברה.
איך?
אוניברסל אקסטריון.
כן, אוניברסל אלג'ברה.
כן. זה אחלס קרקטר גם.
קרקטרים של מה? הצגות של אלגברטי? כן,
בעיקר דיברה על SL2. על SL, כן.
SL2. מה זה קרקטרים?
כן. זה מוגדר באלג'ברה כאילו, זה לא... זה כאילו הסכום...
זה הטרייס של הפעולה ב...
זה כאילו הסכום על המימד כפול כפול אי בחזקת ה-A כאילו די מוזר כאילו, זה לא כאילו...
זה לא כמו בהצגות.
זה לא כאילו בשדה כלשהו.
טוב, מעניין.
זה אובייקט באלגברה מוזרה כאילו.
טוב?
כן, מגניב, אני חייב להגיד.
כן, יש לא מגניב. כן. היא דיברה גם על פאזינג אלמנטס ודברים כאלה?
השתמשנו בהם. זה גם כמה גרסאות. ראינו את זה יש לך כאילו סאב סתם נכון, במכילה 1 ומפרידה נקודות, אז גם כן הכל.
יש לך... אני חושב שהצגות, הקטגוריה של...
אני מכיר איזה גרסה אחרת, אם אתה רק... אם אתה לא סגור, סתם... אתה מסתכל על זה בתור X, כאילו, אז אם אתה מתחיל את אחד ומפריד נקודות, אז אתה צריך להיות צפוף. אבל אם אתה מניח שזה באמת סאב-סטאר אלגברה, אז זה חייב להיות סגור, אז זה פשוט שווה. אחד לאחד, כן, אם אתה מניח שזה כן, אותי, אז הפיור סטייטס את נקודות, ואז פשוט המשפט.
נכון. אם זה מלא פיור סטייט, מה הקשר? כן.
מה זה פעם קומולטיבית? מה זה מוגדר קומולטיבית במקרה הזה? אנחנו נסתכל פה. זה דובר למפתח. למרות שלשאלת את הסיבה של הדבר הזה.
יש. אם תהיה לי רק עוד צריך להסיע, אבל צריך לא. אם אני לא הולך אחת מה? כן, זה מקרה לא, אבל אני אומר, כן אם אתה הולך את זה ככה כן, טוב, מה? מתי שתי סטייטס נותנים את ההצגה? מי יודע את ההצגה? באיזה קונטקסט? שני סטייטס?
אז כדי ההצגות אידיאוגרפיות, הצגות, לשלוח
שהסטייטס הם נראה לי משהו כאילו שהם מיקי קונטיינגים שלנו. כלומר, יש כזה עניין, הגדרה של מה זה קונטיינגים. כאילו זה משהו בפני עצמו. כאילו ההגדרה של ויקטום, זה בדיוק ההגדרה שלנו. ויקטום contained at C, אם יש מה שאתה פי פי, פי C, זה מה שזה ויקטום contained at C, אם ההצגה של פי פי,
כן, אבל
זו הגדרה.
המסביר להם מסך מחדש.
כן, אבל כאילו קשור לטכנולוגיה הפסל, דברים כאלה, זה כלומר, כאילו אם אני מתייחס לזה נגיד כ-positive definite function, אז זה ממש, כאילו זו ההגדרה של תזמתים, זה כאילו, הגדרה אחרת, זה ציון דרך. אני לא זוכר את זה. אבל אז אתה יכול לשאול, מה זה?
אתה ממש מקבל כאילו את המרחב ההצגות עם אחרי כל אתה מקבל אותו כמרחב מנה של הסטייט ספייס. זה לא ציפו.
אין טופולוגי כאילו המרחב ההצגות. האוס. משהו כזה, אני לא באמת יודע. כל מה שאני יודע להגיד זה שיש בהגדרה הזאת. מעבר לזה אני לא... הוויק קונטיינד זה משהו שמדברים עליו. הצגה היא וויק קונטיינד זה משהו, כמעט אתה יודע, כל הפוזיטיב דפנט פונקשן של זה, אבל... שוב, אתה אומר שפשוט מה שאתה אמרת זה כאילו ש... אבל נניח שזה כאילו דבר שזה אותה נקודה.
כן.
כן.
סיימנו לדבר על סופל בינתיים. אוקיי. מיכאל. חסר לו.
יערי חסר.
מיכאל, הנה.
כן.
Okay, so let me share with you my plan for the rest of the course. Yeah, so for now, okay, there are many more things that, of course, we can say about C-star algebra. These are very interesting objects. But we showed right now that any C-star algebra, we can think of it as a concrete one, and the star subalgebra plus star subalgebra P of H. And this is not a C-star algebra course, so my goal is to move to operator systems on which we will speak until a certain point, and then we will go some sort of nice, I hope, nice, okay. And I knew somebody was missing when I started talking. And so and then we have some, maybe probably we'll go to some kind of dynamical results. But right now, before turning into operator systems, which are just, in a concrete way, these are just star-closed subspaces, not subalgebras, just star-closed subspaces, unit of sister arguments. But before turning to them, I want to discuss, just to give you a glimpse about dilation theory. So we can have a whole course about dilation theory. I mean, it's something people like to discuss about and to study, and there are many nice papers, many nice results about dilations, and you're also familiar with at least 2 results about dilation. So let me tell you what are dilations. So some dilations. Definition, maybe. Dilation. A dilation of an operator T in view of H is an operator S in view of K with K some Hilbert space containing H, such that the compression of S to H is D. Namely, such that pH is restricted to H is D. So you can think of it as kind of corners we discussed about these ideas, right? So if I think about, we can always think about, so if I have an H inside of K, so K decomposes as a H plus the orthogonal completion of H, right? And then you can think about an operator as in view of K as a sort of a a matrix, right? Having your A, B, C, D, acting on H direct some H birth. So what is A, B, C, and D? A is just PSP, right? B is just, do you see what, right? This is just a way to think about these things. So for any S, oh, sorry. See how you can put it here? So for any S, I can think of it as P plus P perp. So P perp is I minus P. P perp S P plus P perp. And then we get SP. This P is in fact a restriction into H. So this is something more like PS restricted to it. This is PH restricted.
Or PH star.
Right. Okay. Yes. I mean, depending on how you think about it. Plus PH S restricted to H perp plus E perp. So this is H perp S restricted to H plus E H perp S restricted to H perp. And this means that if you, so if I take a vector, I don't know, in H, and the vector, so right, this will be A in this decomposition, and this will be who?
Or it could be B, right? B.
So
No, maybe.
so this is this is B, right? This is C, and this is D. Right, this acts on. Right, so if I take the composition of a vector sine eta, here I'll get H psi plus B eta, and here's 6 psi plus B eta, and it makes sense. I mean, this part will be indeed in H, and this will be indeed in H perp. So to say that A is a dilation of that S is a dilation of T means that under this decomposition, so this was just something I mentioned here, like a tuta. To say that S is a dilation of T is just to say that under this decomposition, so S is a dilation of T means that under this decomposition, the composition S is nothing but T something. So that's a derivation of an operator. Sometimes people denote this by some kind of, I don't know. Well, this is the most common. Sometimes it's just a potential or doesn't know whatever. Now, in many textbooks, there is something else that is called dilation. I will call it power dilation. Power dilation of an operator T is so this is in some texts. This is called a dilation. So this is power dilation of operator T is a dilation S such that not only that we have pH S restricted to H is equal to T, but we have it also to the powers. So for any power n here, for every n. So example, if this dilation is not of this form, but let's say if it is of this form, then automatically this is a power dilation, right? Because if you take powers of this, then it will correspond to powers of this in a nice way inside the matrix. I'm not saying this is the only way. I'm just saying this is an example. Of course, also this one is zero. So the case in which this guy is zero is called an extension. I mean, the dilation such that this guy is zero is called an extension. A dilation such that this guy is zero is called coextension. But do you have a question? And I'm just if I would use it, I will write it explicitly right now. I'm not writing definition of extension and coextensions. Okay, and I can also, so these were dilations of an operator, but I can also speak about dilations of linear maps. So a dilation,
So both zero in the left, lower left, and in the both extension and co-extension, or how does it? This is what
both I mean extensions are power dilations.
also co-extension.
What? Also co-extension. You don't need to be both extension, co-extension, which is of course also. A dilation of so maybe yes. Okay, example maybe. Right, S is equal to, and you figure out what way, right? Something like this. Because if you take power of them, a dilation of a linear map phi from A to B of H, let's say the sister algebra for now, is a linear map psi. Note that I'm not speaking about staromorphisms though, okay? Just linear maps. Is a linear map psi from A to B of K, K containing H, such that phi of A is PH, psi A, restricted to H for any A. So I can speak about dilations of maps. Example. One. Any state dilates, מתנפח, into a star representation. Right? This is what? GNS.
Yeah.
That's the GNS. Right? The GNS tells us that if you start with a state, so it goes from A to C, then you get a star representation. And we explain why to put psi phi and psi phi inside in a product is like compress it into an identification of this psi phi as a vector in K. Right, so it is a vector in K.
Mm-hmm.
I identify C and span of psi. Two, today we showed that any pure state dilates into an irreducible star. So if and later next week or next week, one of the things I will show that in fact something that is called UCP, unit completely positive map, dilates into star representations. So if there is an object you understand very well, like star representations, we understand them very well. I mean, we know exactly, in some sense, what are star representations. We understand them well. They are well behaved. They are very rigid. We know them very well. And we have an object that we don't know well, but it dilates to an object we know well, then this is very good. Because we can sometimes dilate it, understand everything we need to know in the bigger picture, in the bigger metric somehow, and then restrict it back and do whatever we need to do with these. Okay, so this would be a theme that we will have in mind. And somehow, before moving to this thing, I would like to give you something that is much fundamental, like to speak about the relations of an operator. So this was, I mean, this happens chronologically, maybe parallel to the GNS, I don't know, but of course, in some sense, in some pedagogical sense before the GNS. I mean, maybe it happens after, but that's not the point. I mean, I think it's from the 40s, maybe before the GNS. So that's almost an exercise. So let's discuss about relations of operators. So first, what are the best operators in the world? Well, sure, but in an operator theoretical sense, scalar operators are very good. And if we want to pick more than that, diagonal, of course, are good, but also unitary operators. We really like them, we understand them well, we understand their spectrum, so they are normal, they're invertible, they're inverse, right? So these are very nice operators. And here is the first dilation I'm going to show you, which is very easy. Assume V is an isometry. So V star V is I. Then note that what can I say about the difference? Sometimes it is called the defect, but okay. So this is V star V, this is V star V, but what happens if I take V star? What can I say about this guy? So I claim it's easy to see that this is a projection, right? So anyway, it's self-adjoint. So now that this is self-adjoint, and I take you will have V star V in the middle, right? It will be this minus this, and then minus V star, and then plus V star V star, right? But this is I. So altogether, this is okay. So what can you tell me about this guy? U, which is a big hint. V and I minus V star and V star and 0. So this is by definition a dilation of V. It's even an extension of V. So it is not. It won't be only a dilation of V. It is a power dilation of V. Okay. So U is a power dilation. Is a power dilation of V. But let's check what is U star and U star U. But U star U is V star I minus V star V 0. Yes, maybe we should verify that the composition I discuss about behaves well with star operations and multiplication and everything. Okay, so I can do the star and I can multiply these blocks. So this is V star V, right? And this is V star minus V star V star. And this is V minus v star v, and this is I minus v star square plus v star. So this is I, this is 1, so this is 0. This is also 0. This is a projection, so it is equal to this without the square, so I get 1. So U star U is 1. And similarly, to the computation, U star is also 1.
And this is like
So U is unitary in U of A plus H. Bartolo?
kind of clear that the first column preserves the norm and also the second one. Kind of
Again, please. What?
no, never mind. So just to see why it's unit.
Why it's unitary? Ah, you
And
say.
when you restrict to H, you know
Yes.
it's an isometry, so it preserves the norm of the vector in H.
Right.
And also in H perp.
Okay, you wanted to see it from the norm. Okay, I see. Sure.
I'm just saying that, like, here you have the projection onto the orthogonal complement of the image of V, and here you have, like, V star is just the co-isometry taking the image of V. So this is the complement.
Right. Right. No, right. You can think of it. Okay, there are many ways to think about it.
No.
Just know that we just show that any isometry dilates to a unitary, right? Not only dilates, powder dilates to unitary. Okay. Remember this. Now, let T be a contraction. Contraction means that T is in the unit pole. So usually that's the way I denote unit pole, okay? I don't know if I did this before, man, probably. So again, I'm defining the defect of T, which is I minus TT star. In fact, you should take a square root over it. Before it was a projection, so I didn't mind, but that's somehow the right way to do it. And now I'm going to play the following game. So no, I want it now to be T star T. And now I want to play the following game. First, note that T psi square plus D psi square is what? When this is psi T star T psi, right? And this is psi 1 minus T star T psi, right? Because they have half and they can. So altogether, this is a psi psi. So what is B? So I'm going to dilate it not only to H plus H, but to H plus H infinitely many times. So to something like this. So what do I mean by this? By this I mean, what is this guy for you guys? I mean, sometimes algebraically people think about infinite direct sums as a direct sum that takes only finitely many elements. But in the category of Hilbert spaces, you usually complete them. And if you complete these, so when I denote something like this, I mean that I already completed it because that's the convention for Hilbert spaces. And then you get something that sometimes is also denoted by L2 of H, which is what? Which is a like space of all sequences psi n, and in n, such that psi n norm square is finite. So and this is a Hilbert space. The inner product is psi eta. I mean psi n with eta n. Inner product is nothing but the sum of the inner products. So, what's going to be the dilation? Let me tell you. I mean, okay, maybe I can write in a matricial form, but maybe let me write it what it does to. Okay, so let me define V. So let's define V on B of H infinity by. So V of psi1, psi2, psi3, etc. This is going to be fix psi1 dt psi1 and then psi2, psi3, etc. So I use the fact I have infinitely many coordinates to push everything, and then in the first two coordinates I put t psi1 and dt psi1. Because of this, V is an isometry, right? Because of this argument. So V is an isometry. Let me write this in a matrix form. So it's going to be an infinite matrix, but still, I mean, the same concept is going to work. In a matrix form, V is T, and I'm going to have so dt, and then just write like I like this. Right? Is it clear? I mean, and whenever I don't write anything, it means that it is zero. I don't want to fill everything with zeros, but
You have to take infinite dimensions.
I mean, what do you mean by F2? But right now I'm taking infinitely many dimensions to be able to put everything.
כן, חזק. מה?
No, it's fine. Joking.
שלא תאשים את עצמך בדברים שכבר יש, בסדקים שיש.
כן, יש סדקים? So what did I want to say? Okay, so right now we need to push it, and we can ask ourselves later, did we really need to push it into infinitely many dimensions? But I'm really using it. I mean, to be able to get this. So note that this is of the form, right? So this is of the form T, 0, something, something. So it's power dilation, right? So take power, isn't it?
Maybe we can do the same thing that we did in the first example, right? Because this is an isometry.
Yes.
So we can
dilate it. Of course, we can concatenate our dilations. So this is a power dilation. So this is a power dilation. This is a power dilation, and okay, this is such a form is called the colex. Okay, and good, and the corollary. Well, this is originally due to Nash. That's the way to write his name, but you pronounce it Nash. So it's called Nash dilation theorem. Any contraction dilates, power dilates. To a unitary. Our dilation is a transitive relation. Okay, you can check that if y is a power dilation of x and z is a power dilation of y, then z is a power dilation of x. Right? So check. I mean, there's nothing to check. It's not even an exercise, but if you want to verify it. Good. So I mean, check it. No, not check it. Use no, for that. Use the two dilations, or maybe concatenate. To the dilations here, to dilations you mentioned. Okay, so that's this is very cool if you think about it. You start with a contraction, and suddenly you can dilate it into a unitary. So what can we do with this? Many things we'll see in the course later, but right now let me show you something that is really immediate. A corollary. And by the way, before the corollary, let me just comment that remark. So do I really want to remark it now? So this also answers to Ben's question somehow. There is a sense of okay. I said any contraction power dilates to unitary, but there is also some kind of rigidity. There is also something like called minimal unitary dilation. So I can do it in a minimal way somehow, and then any two minimal unitary dilation of a contraction will be the same. So there will be a unitary between them such that everything will commute, and the unitary will be the identity on the space H, on the small space. Okay? We can show it now, but in fact we will get it for free later. We'll get it for free later. So I'm thinking maybe not to do this part now. So let me just write a comment about it. So there is a notion of a minimal unitary dilation. So דרך הכי חסכונית שבה ניתן למצוא יוניטרי, and under certain identification, minimal unitary dilation is unique.
חסכונית in the sense of the size of the Hilbert space?
Yes, is unique. We'll get it for free later. We can prove it now. I mean, it's an X. If you want, you can prove it. We can prove it now. But we will anyway get this for free. Get this for free later. I mean, after science, okay, later.
Guy, when you say we can prove it now, what do you mean by it? That it is unique, or
The unique. I mean, we should define this minimality and then prove that it is unique. We should define the identification. In fact, I think, I mean, if you have free time and you go home and you try to define it, you'll get the right definition. It's not hard to do it, but okay. So corollary, not from this remark, from Nash dilation theorem. Corollary. The corollary is called von Neumann inequality. Von Neumann inequality. For every T contraction and P a polynomial, P of T, it's known, is less than the supremum of the polynomial over the unit circle. Can you see the proof?
The maximum principle of
Then
בטוח זה התרגיל במורכבות בצורה כזו או אחרת.
So this is not the issue. I mean, if it was z less than or equal to 1, okay, let me write z less than or equal to 1. I mean, that's not the issue. You're right. I mean, if you prove it for z less than or equal to 1, then you can remove the maximum principle to say it's on the boundary. But that's not the question. So I may even show this.
We should dilate for unitary and then use the continuous functional calculus.
So exactly. So and what do we know about the spectrum of a unitary?
The unit circle.
So why, by the way, have you all happened to think about that the spectrum of unitary is inside the unit circle? You see it in functional analysis. So you can verify. So if you've never thought about it, think about it for 2 minutes. Why for every lambda not in the unit circle, lambda minus u is invertible for unitary u? That's an easy accuracy. So and dilate or power dilate a t into a unitary u, and since spectrum of u is in t, verify
verify you know why. We know that P of U is exactly the supreme right over lambda in the spectrum of U of P lambda, right? But this is less than or equal to the supremum over lambda 1 lambda. And since we're speaking about the power dilation, so power dilation means that you have this dilation on the whole polynomial, right? Because you have it on the whole power. And pH strict into a, this is PT. So and so PT norm is less than Q. Yes.
Can't we use functional calculus only on self-adjoint elements?
Only on normal elements. You need a sister algebra to be commutative.
Okay.
So once you have a commutative sister algebra, the commutative sister algebra generated by this element. And so and you do have them exactly for normal elements. Then it can be a So now, here's an interesting question. I mean, consider this very nice theorem of von Neumann. Think about it. So for von Neumann and also for other people, this inequality is interesting also for 2x2 matrices.
Mm-hmm.
But its proof somehow goes into the infinite dimensional world. Although it says things only about finite dimensional things. So here there's a nice question, like, and that's a question that many people really like to think about. Do you really need infinite dimensionality to prove this or to think about such inequalities? Not only this, there are also other versions, other games that you can do. And at the end, the result is very finite dimensional. I mean, may be very finite dimensional. For example, here you can consider this for matrices. Can you have a finite dimensional proof? So I don't know all the answers, but these are interesting questions. And okay.
Wait, but people I think ask here a concrete one, right? Like whether you have a matrix which is minimal unitary dilation.
That's a different question. You're asking, giving me a matrix that is a contractive, that is a contraction, is there a unitary dilation of it that is finite dimensional? I ask something else. I ask, can you get von Neumann inequality even when it is infinite dimensional, the unitary dilation? Like, do you have another proof? Okay, there are many proofs. I know at least 3 proofs to the von Neumann inequality. All of them passes through some kind of infinite dimensional techniques. But I think there are different proofs. But okay, maybe we can read about this. Yes, and your question is of course a concrete question. When does I don't know, contraction as a like finite dimensional contraction as a finite dimensional unitary division, of course. Question you can always ask. Okay, now so let me start our discussion about operator systems and there's also Andrews dilation theorem, which is really nice, but I will not present, I think. It tells us that if I have 2 commuting contractions, I can dilate them jointly to commuting unitaries, like power dilating them. And you cannot do it for 3 commuting elements. And there are counterexamples for that. Oh. So operator systems. And unit of positive. Implicit positive. Maps. Before defining what an operator system is and what a completely positive map is, whenever we have a sister algebra A, if A is a sister algebra, so I claim that together with A, there is an infinite family of other sister algebras, which are these guys, Mn of A. So an element in Mn of A is an n by n matrix, such that each entry is in A. And how do I multiply 2 elements here?
Point. No.
Like matrices, right? So AIK, BKJ. And what's the star? Well, you know what's the star, right? And so Aij star is nothing but Aj I star. Bit. What about a norm?
Wait, you don't need to transpose it in some sense? Ah, yeah.
The transpose them.
Yeah.
What about the norm? So okay, so I showed you this is a star algebra, and it has a norm. Well, so now I'm going to do something that has to do, like I'm going to do some choice, and then I'll tell that the norm is independent of the choice somehow. So by the GNS, by the corollaries of GNS, the Gelfand-Naiman, we can faithfully represent A inside B of H. So of course there is a representation here, but a faithful representation, but I write it like this, okay? So faithfully represent A inside B of H. Then Mn of B of H, you can think of it as B of n copies of H. Right? So what does an n by n matrix does to a vector, which is n vectors? You know how it acts. So you understand this? So do you understand this identification, or do you need more? Please tell me if it's not clear. Is it okay? So an n by n matrix, right? You have a T11 until T1n, Tn1 until Tnn. How does it act over something in here? Something in here is just n vectors. Well, it does what it has to do, right? So and this is, I mean, an isomorphism. And but this guy is the operator norm. And if A is in B of H, then M and A is inside here. So M and A sits inside Mn of B of H, which is isomorphic to B of H to the N. Thus, we can endow M and A with this norm. Verify that this norm satisfies the C-star identity, and then I claim after we verify this that this norm was independent of this representation. A priori, this norm is dependent on this representation, right? If somebody else chooses another representation, then maybe I get another norm. But no. So this is the general fact that I mentioned before. If I have a C-star algebra, then it has a unique norm. You cannot give it another norm so that it will be C-star algebra. Why? Because of what? Right, okay. Right, so every monomorphism, every star monomorphism is an isometry. So the identity map will be in isometry, so the norm is unique. Another way to see it, I mean the proof of this thing is that the norm comes from the algebra. It comes from the spectral radius. So the algebra knows the norm somehow. So once you show something is a C-star algebra, like you find the norm on it, then that's the unique norm. There isn't another way to norm it. Okay? So verify this norm satisfy sometimes such norm is called a C-star norm, satisfy C-star identity. Then it's an independent on the representation of A inside B of H. Why? Because a norm on a C-star algebra is determined by the algebra. Hence unique. Right, on a positive element is the spectral radius, and this gives you the normal somehow. Or what Alon said, every star monomorphism, in particular the identity, will be isometric. Okay, good. So, right, so every C-star algebra comes with a bunch, infinitely many people, infinitely many other C-star algebras. Okay. Now, let me just maybe write here A square is equal to A star A, which is rho. Conclusion. Every C-star algebra carries an extra an extra information of a metric structure each equipped with one, a canonical norm. Canonical in the sense that we explained before, it does not depend on. But now, once it's a sister algebra, then each sister algebra has its positive elements. So now each of these M of A has its positive elements, right? So it has an order on the positive elements, so it has an order. So canonical. Coming from positive elements.
Fine. The order won't be some product order because you can you make it diagonal and get the product order on the some eigenvalues, or it is not. So is the order decomposes to some product order, or it is maybe?
What is the product?
I don't know, like maybe smaller in every coordinate, etc. Some.
Not everything is.
So you're saying so. Of course, if A is less than B, then of course I know, and C is less than D, then diagonally, of course this, for example, will be less than this. Of course there is a relation between the orders somehow, but it's not that in general, I don't know, pointwise less than or equal will be, okay?
Will you be able to diagonalize self-adjoint elements into like a matrix with self-adjoint elements on the diagonal?
So why can you do it?
I'm asking.
No. There is no reason in general. So
Why do you say there's no reason to?
So what is a normal in this sense? Why do you like?
Even self-adjoint, say self-adjoint. Why?
So self-adjoint, yes. So what? So what do you want to say? What can?
Sorry, I don't see immediately why you shouldn't.
Well, it's not clear what you mean by diagonalization. In fact,
we could talk about unitaries in the matrices of A.
Okay, so you're saying so you're asking now a question. You're saying, okay, Michael is asking a question. Suppose that I take a matrix A, and I know that A star commutes with A, say, or A star is equal to A. Can I find Unitarian Mn of A such that U star A U will be diagonal? That's the question. And so, I don't see. Right. Let's think about the usual case, the complex numbers case. Why is it true over there? It's true over there because something. Well, I don't see how this should work in sister algebras in general, right? It's very weird, and it will work. But we can think about it, and that's a good question, maybe. Yes. Okay. Anyway, in general, this comes with the canonical order. I just want to finish something before we leave. Then I'm not going to see you for 2 weeks. So So what did I want to say? Okay, so what I want to say is that now philosophically consider this structure and ask yourself what is the right object, categorically speaking, that encodes this. So definition. Let A be a unital sister algebra. A subspace S in A, subspace. I'm not claiming it, I'm not going to require it is closed at this point, such that S star is the not the dual space, but all the stars of elements in S, such that S star, which is all the A star in S, is in S. So S is star invariant. And one is in S. It's called an operator system. And before giving you some examples of these, I want us first to check something. So note that every A in S decomposes into a linear combination of two self-adjoints, as always, right? A is equal to A plus A star over 2 plus I, A minus A star, right? Over 2I. And each of these guys is in S because of this. Second of all, every self-adjoint A in S. So there are plenty of self-adjoint in S, right? Because of this. And every self-adjoint in S decomposes into difference. That's the way you flash. Difference of two positive elements. Now be careful. I can decompose A to A plus minus A minus as before, where A plus and A minus are the A plus and A minus that we know that that we have in a sister algebra A. Because it's not a sister algebra anymore, but we have one. And I reminded you back then that when we have one, there is a very simple decomposition of an element into two positive elements. I can always write it as a half times A norm plus A minus half, or like this, A plus A, A plus A minus half A minus A. And here I use this fact. That one is right.
always mean.
Because norm always means, yes, a number is for us just another way to write. Okay. Be careful again, in general, we don't have the spatial decomposition, this unique decomposition that right in this decomposition, also the product of these elements are zero. Here, no, it does not. Okay. So every element in an operator system is the linear combination of 4 positive elements, right? So you see that S knows its positive elements. Also, okay, so this was 2 remarks. Another remark, if S is an operator system, then automatically Mn of S is an operator system. So these guys, these operator systems, somehow they get this norm structure on every, they get this level structure, they get this norm structure, and this positive order structure on all of the levels. And the positive elements of them knows everything about them. Every element is a linear combination of 4 positive elements. Okay. So examples. A nice example that we will use here and there is just the span of 1 Z and Z bar inside C of C. So this is S. In general, if S in C of X is an operator system, then S is called a function system. And any sister algebra is, of course, any sister algebra is an operator system. Note that
we're talking only the unital ones, right?
right, everything is unital. Right? When we speak about operator systems, the unit is crucial to this discussion. Another remark: if we have a map phi between 2 operator systems that is linear, is a linear map, then I have a map phi n from Mn of S into Mn of T that map Sij into phi of Sij. If you know about tensor products, you can think about Mn of S as Mn tensor S. And then phi n is just the identity tensor, like the identity on Mn tensor phi. Is there anybody here who does not know a little bit about tensor products? let's say algebraic tensor product of Hilbert spaces. Okay. So definition. Let S and T be operator systems. Let phi from S to T be linear. Phi is positive if A is greater than 0, implies that phi of A is greater than 0. And positive if phi n is positive. Completely positive if for every n it is n positive. If n positive for every n. Phi is contractive. So you know what is contractive? If phi norm is less than 1, and contractive if phi n norm is less than 1, and completely contractive if n contractive for every n. And maybe let me mention also this, phi is, well, you know what is bounded. Okay, now, if phi is bounded, then phi n is automatically bounded too. So if phi is bounded, phi n is automatically bounded too. So if you think about the tensor product picture, then this is immediate. If not, then it's also an easy exercise. If there is an M such that, or if supremum over all n of the norm of phi n is finite, call this the CB norm of phi, then phi is called completely bounded. Bounded. So I'm happy that I had the time to write these definitions, because what we're going to do next time is to start from this point that we know what are operator systems, what are these maps, and then we'll start to investigate, I mean, what can go wrong between them. So do we have maps that are positive and not completely positive? What's bad with these in the sense that are interest us? And I hope to convince you that these objects, together with completely positive maps, are very natural and very interesting. And another thing I would like to, and maybe I will tell you also about the history about these. I mean, there is a very nice story about how completely positive maps came into our life. Okay, last thing before we leave is is to tell you that I did something that in some sense is very not coherent with what we did when we discussed about sister algebras. So when we discuss about sister algebras, we define an abstract version of sister algebra. The sister algebra is an algebra, right? A Bannister algebra satisfying inequality. And then we said that every abstract sister algebra is a concrete sister algebra, like it is a star subalgebra, a closed star subalgebra of U of H. Now I defined an operator system to be a subspace, a unital self-adjoint subspace of, if you want, B of H, right? The sister algebra of B of H. Like I defined it concretely. There is a way to define it abstractly, like to give you a set of axioms. And maybe, so what I have in mind, this is another thing that we didn't discuss about. So right now there are 17 or 18 people that are registered to the course, but I don't know, how many of you want to get a grade on the course? There is no grade, it's just a fail or pass, but still.
Not sure yet.
Okay, because my original thought was if we have a reasonable number of people, where reasonable is a number less than, 6, 7, I don't know, I think. Then in addition to the homework, then the homework will be worth half of the grade. And then you'll also need to give a short presentation. Yes, and then a reasonable talk can be about these abstract definition of operator systems. So to define it and then to show us this is due to joint efforts that every operator system, every abstract operator system satisfies the concrete definition that we gave today. But if there will be, 17 students that wants to be registered, then we won't be able to have write presentations. Okay. See you. Have a happy Hanukkah.
תודה, גיא.
בבקשה.